Okay, so when you have a moment, you're going to add this to your vocabulary packet. We're going to talk about rotation. Bless you. A rotation is a transformation in which the figure is turned about a fixed point. That point is called the center of rotation. And then rays drawn from the center of rotation to a point and its image form an angle of rotation. So in this picture here, the image is this little flag-like thing. A little flag, okay? And then the center of rotation is this point right here. And then the rays connect to the edges of the figure and form an angle of rotation. So what degrees did this particular figure rotate? It says it. 40 degrees. Which direction? Counterclockwise. So right here it says the figure above shows a 40 degrees counterclockwise rotation. Rotations can be clockwise or counterclockwise. In this chapter, all rotations are counterclockwise unless otherwise noted. So this is kind of different than what we were doing on Friday. On Friday we were doing all clockwise. In this particular chapter, we're going to do counterclockwise. As a teacher who teaches things past geometry, counterclockwise is used way more in math, which seems so weird, but it is. I teach pre-calculus, and we do counterclockwise rotations all the time. All the time. Okay. So we have coordinate rules. You guys were supposed to figure out coordinate rules, but you were finding them for 90 degrees clockwise, or 180 degrees clockwise, 270 degrees clockwise. These are the given rotations for counterclockwise. So these would be the ones that you use for your assignment today. Do we need to go over them? Jay, what's this one mean? What do we do from here to here? Okay, so you switch the order. Is that all? You switch the X and Y order. Is that all? There's a negative on which value? The B, which is the original X or Y? The Y value, right. Okay. All right, we're going to graph quadrilateral RSTU with vertices at 3, 1. Why is my thing all fuzzy? There we go. Vertices at 3, 1, 5, 1, 5, negative 3, 2, negative 1. Oops. 2. Okay, so I'm going to do this using the 4 ordered pairs, and I'm use the formula from the previous page that says for a rotation of 270 degrees, AB changes into B, negative A. So if AB changes into B, negative A, then 3, 1 changes into 1, negative 3. 5, 1 changes into 1, negative 5. 5, negative 3 changes into negative 3, negative 5. And 2, negative 1 changes into negative 1, negative 2. So I switched the y value to the front, did nothing to it. I switched the x value to the end and changed all the signs. And then I went and I labeled my picture as R prime, S prime, T prime, U prime. Now you do not have to do this every time. If you're using, you have to do this every time. But if I take like point R, and I draw a straight line from R to the origin. And I also draw the straight line from R prime to the origin. These little helpers here, these little rays, should form what angle? 270. That means I got to think around this direction. Okay, so 270 degrees counterclockwise. What would that mean if I was going clockwise? 90 degrees. So even though we're going 270, it might be hard to look at 270, but if you look the other direction, it should form 90 degrees. And that will work with any of those points up there, not just R. That will work with every single point. Okay, try triangle K or JKL. Vertices at 3, 0. 4, 3, 6, 0. So we go and we look at our coordinate rules for 90 degrees. It says negative BA. So I'm going to copy that over, negative BA. Then I'm going to do that to every single point. So I'm going to flip the 2 points. I'm going to switch the 2 points. And the y value becomes negative. But only really one of them mattered for becoming negative. 0, 3, negative 3, 4, 0, 6. And I can use 2 little helpers to make sure that it looks right. Which, what do you think would be an easy one to look at? JKL, what do you think? There's something out there. John? J? Okay, because that one's already drawn for me. Right? It's like right there. If you really want to make sure, let's look at K, because that one was not drawn for me. Does that seem like it went 90 degrees counterclockwise? Yes. Questions? Rotation's way too easy for you. We need to make it harder. No, you like it easy. Okay. All right. Postulate 4.3 is a rotation is a rigid motion. In your own words, what does that mean? Write it down. In your own words, what does that mean? I'm going to call in some people. give me their answers. In your own words, what does that mean? You want me first? Okay, in your own words. We've talked about rigid motions before. There are a couple people that had nothing written. We're going to go check them again. No, but I didn't know what it said. That. Okay. Matthew, what'd you put?
I said the image of a rotation stays the same shape of the pre-image.
Stays the same shape of the pre-image. Excellent. Aaron, what'd you put?
Rotation does not change the size or shape of the pre-image.
The rotation does not change the size or the shape of the pre-image. Alexa, what'd you put? Oh, it moves to a different spot, but it doesn't change size. Good. I forget who said what. John, what'd you put?
That the rotation doesn't change the size or the shape of the image.
Doesn't change to the size or the shape. So nobody put like one major word in there, or at least nobody had, when I had walked around, that put no a major word in there, and that's probably because I said to do it in your own words, which is fine. You guys did a really good job. Those of you that I called on, and most of you when I walked around. The two figures are what? What does it mean when they have the same shape, size, measurements? What? Congruent, yeah. I don't know why my handwriting is so messy right this second. Two figures are congruent. Only because I'm using a pen that does not erase. That's why it's so messy. Okay. Now let's do some composition functions. I actually don't want to spend that much time on this because I feel like you guys are getting this, not a problem. Let's try graph RS, the first one, graph RS, with endpoints 1, -3, 2, -6, and there is a composition, meaning there's two things that you have to do. Bless you. So I've got RS. It says we have to reflect in the y-axis. If I'm reflecting in the y-axis, I'm trying to make that skinny. If I'm reflecting in the y-axis, that means going over the y-axis. If I'm reflecting in the y-axis, what changes about the ordered pairs? This is one you don't have to memorize, because you can look at it and figure it out if you just use some common sense. If I'm reflecting in the y-axis, from RS here, where's RS going to go? David, where's RS going to go? Sure. Third one, yeah. It's going to go over to the third one. So what of the two coordinates is going to change? Will the x's change or the y's change? The x's change, because even though I say I'm reflecting in the y-axis, that's moving horizontally. Okay, it's reflecting horizontally. So my y values change, or x values change. They go from positive to negative. So if I'm making like a rule, I would say that AB goes from AB to -AB. So I can write those ordered pairs as -1, -3, -2, -6. Or I can go and just graph them on the graph. I mean, you don't have to write the ordered pairs. I'm just showing you that you can. So that would be my R prime, S prime. And then we have to take that and go 90 degrees about the origin. So now I'm going to look back on that first page that has all my rules on it. That says 90 degrees is -BA. So for -BA, you do not go back to the original. Ignore the original. We just go back a step and we go to the ordered pairs that we just graphed. So I put those in green. I'm going to look at the green ones, and I'm going to do -BA. So I'm going to have 3, -1, and 6, -2. Do you guys think if we switched the order of reflection and rotation, would it end up in the exact same place? If we switched the order and did the rotation first and then the reflection, would it end up in the same place? Question? I'm just letting everybody have a chance to think. If I took my purple RS and I did a 90 degrees rotation first, where would that end up? It's 90 degrees counterclockwise, this direction. Where would that end up? Approximately. You don't have to tell me the order of pairs, but where, Lynn? You can tell me the order of pairs, if you know them. So what quadrant would that end up at? In quadrant 1. So then if I did a reflection second, where will that end up? Oops, double prime. Not even close to where the first one ended up, huh? So the order does matter. It needs to go in the order that it's given to you. You saw me do it right here. These are not the same. Okay, you try. Graph triangle TUV with vertices 1, 2, 3, 5, 6, 3. All right, I haven't finished it yet, but I want to pause and ask you guys a question. When you do something like 180 degrees rotation, why am I asking you to check that angle? Why was I asking you to do that earlier? What do you think? There's got to be a reason why I said that. You connect point T, or any points, you connect point T to the origin from both figures. When you connect point T to the origin from both figures, you can see that that makes 180 degrees. So that's validating that I did it right. Why do I think that's important to go over? Why would I spend 5 minutes going over that? Rakai, do you know why I'd go over this? Because rotation's what? Right, but why? I mean, I use the points over here. I use the, what's this called? The rule. Why do I want you to also look over here? Lynn, do you know why? To check in also what? Yeah, so my biggest thing is to check, because could we possibly make a mathematical error accidentally? I do it all the time, okay? But when I go over and I look at my picture and I say, ooh, that doesn't look like 180 degrees. Or maybe 2 of the points were right, but the third point makes it not look like the same triangle anymore. We need to know that these triangles should be congruent. So if it's not congruent, I've made a mistake somewhere. That's your guys' job. I don't want you to turn into me something that has a teeny little triangle over here and a really big tall triangle on this side. So you should know that these should be the same. So we got to keep thinking about that. I did the first one. I did the points for the second one. I'm finishing up the points. So go ahead and finish yours up if you didn't finish it yet. See, I know I made a mistake. What am I doing wrong on this one? Oh, I'm thinking about the wrong one. What? This one? I keep feeling like I'm messing it up. I'm supposed to keep the same A. Yeah, I don't know. I just kept feeling like I was messing it up, and then I had it right originally. Keep the same A, change the Y. I know what was going on in my head. I was for some reason thinking I had to flip this one, but it's really the green one that's flipping. That's wrong. Okay. And then -6, 3. There you go. See? I talk about making mistakes, and I made 2 of them right in front of your face. Didn't do that on purpose. That just happened. Lucky you. Okay, last section talks about rotational symmetry. A figure in a plane has rotational symmetry when the figure can be mapped onto itself by a rotation of 180 degrees or less. 180 degrees or less about the center of the figure. And the center is called the center of symmetry, which I believe, no, we had center of rotation. Center of symmetry would be in this case. Note that the rotation can be either clockwise or counterclockwise. For example, the figure below has rotational symmetry because a rotation of either 90 degrees or 180 degrees maps the figure onto itself. A rotation of 45 degrees does not. So then they've got examples where the original figure is right here. If we rotate it 45 degrees, does it match the original figure? No. But if we measure 90 degrees rotation, now these two look exactly the same. Or if we do 180 degrees, these first ones and last ones look exactly the same. So this has rotational symmetry. The figure above also has point symmetry, which is 180 degrees rotational symmetry. So anytime you have point symmetry, that is when we have 180 degrees rotational symmetry. Okay, so does the figure have rotational symmetry? If so, describe any rotations that map it onto itself. So we're going to look at the center of this parallelogram. Could we turn this parallelogram 90 degrees? 45 degrees, 180 degrees, and it'll land on itself. What do you think? Yeah, what? 180? Anything less than 180? Ryan? Nope, just 180 degrees. So this does have rotational symmetry, yes, but it's only 180 degrees. How about a regular octagon? Regular means that all 8 sides and all 8 angles are the same. This is like a perfect octagon. So we look at the center of this octagon. I might even look at these diagonals formed from the center to each point to help me. If I rotate this point to here, will the entire octagon map on itself? How many degrees did I just rotate it? 45? How are you getting 45? I'm not saying you're wrong. How are you getting 45? Lucky guess. How can we figure out how many degrees this rotates from one corner till it matches up the next corner? How many degrees around the whole thing? Oh no, we don't know that. in a circle? Do we know how many degrees in a circle? Austin, how many degrees in a circle? Austin. Poke him. You're the closest. Austin, how many degrees in a circle? How many degrees in a circle? Yeah, how many is that? 360. Okay, somebody asleep knows the answer. You're not sleeping in my room. If you would like to stand, if that will help you not fall asleep, you're more than welcome to stand. Okay, then don't fall asleep. Braylon. 360 around the whole circle. How many of these same places are there around the whole circle? How do you think I would find the degrees for one of them? Avneet's going to tell us the answer. Thanks, Avneet. Do you know what 360 divided by 2 is? Half a circle? 180? So what's that divided by 2? $180 divided by 2? I can't hear you, hon. Here's 180 degrees. Divide that by 2. It is 90, yeah. So divide that by 2. Okay, so 45 degrees. Is that the only rotational symmetry? Just 45 degrees? Nope. What if I went 2 of them? What would that be? 90. What if I did 3 of them? That would not be 180. What if I did 3 of them? What? How much is one of these? How much is one of these, Maggie? How much is one? 45. So plus 45 is 90. Plus another 45 is 135. How about if I did 4 of them, which is half the way around? 180. Rotational symmetry is listed by angles that are equal to or less than 180, so I do not have to go past 180. Trapezoid. Here's the center. If I rotate this trapezoid, how much do I need to rotate it before it matches up with itself again? Okay, so if I rotated this, you can see, oh, and I gotta fold away this sticky part. You can see underneath it, okay? Yeah? Yeah, you can see underneath. All right, so if I rotated this, try to keep it on the center. Tell me when it matches up with itself again. Well, there's 180 degrees. What do I know about rotational symmetry? What does it have to be less than? Has to be less than what? 180. So I already went past 180. I have to go full 360 before it matches up again. So does this have rotational symmetry? It does not. Has to match up at 180 or less. How about rhombus? This thing's kind of helpful. Rhombus. Cameron, what do you think? What? Yeah, what? Of how much? 180? Okay, so I'm gonna like turn it. There's 90, didn't match yet. Turn it to 180. Yes, that does work for 100. It has to be 180 or less. That was the smallest one. Rotational symmetry we had. Here is another octagon. This is concave octagon. What do you think? 90? If we're looking here, it's going to match up when it goes to here. Is that the, oops, that was bad. Only answer, 90 degrees? Only answer? Donovan? 180, good. All right, last question. This particular right triangle. I don't even know where the center of that right triangle is. Maybe here? Are you thinking what I'm thinking? Okay. All right, your assignment is Big Ideas Online. You have 10 minutes. You're not going to sit here for 10 minutes. 10 minutes. Online.